Hello science family, this is worksheet number 2 for single replacement type reactions. And hopefully you already have a better understanding of how single replacements are working, but do recall that the initial metal in the reaction is by itself, and it's going to challenge the metal in the ionic compound. If potassium ends up being stronger than barium, then barium will go out by itself and potassium will come in and bond with sulfate. So to figure that out, we have to look at the activity series over here to the right. So we're looking at potassium, and potassium is up top here at the chart. And we're looking at barium, which is just underneath it. And if you take a look at that, potassium is higher up on the chart, so therefore it's stronger. So what does that mean? That means that potassium will come in and it will kick barium out. So now we have barium all by itself. And the new compound is going to be potassium, and that's going to now be combined with the polyatomic ion called sulfate. All right, so I finished my word equation first. All right, and now that I have that whole word equation, I'm going to write out my chemical equation. So first of all, potassium by itself is just K, right? Barium and sulfate come together, we have to look at their charges. If I look on my ion sheet, barium is a +2 charge and sulfate is a -2 charge. So when potassium's all alone, it's just going to be K. And when barium and sulfate come together, because it's +2 and -2, they are just going to come together as BaSO4. All right, now barium over here on the product side is by itself, so that's Ba. But remember, potassium and sulfate, when they come together, they have different charges. Potassium's +1, and sulfate is SO4 with a 2- charge. So when those two come together, you're going to need 2 potassiums for every 1 sulfate. So let's write this chemical equation. Barium's going to be by itself, and then we're going to have potassium. You're going to need 2 of them to cancel out with the sulfate. And let me erase that sulfate and write that in. Here we go. So K2SO4. Now that I've written that, I just need to make sure that everything is balanced, all right? And everything looks good except for the potassiums. I have 2 potassium over here, so it looks like I'm going to need to make 2 over there. And as long as I do that, everything else seems to be balanced out. 1 barium, 1 sulfate, 1 barium, 1 sulfate. So we're good to go. So you did a single replacement reaction, barium and potassium switched, and the reason being is because potassium was stronger than barium. All right, if we cruise to number 2, we can look and see that magnesium is going to try to react with calcium nitrate. The question is magnesium stronger than calcium to knock it out? Remember, the metal ion, cation magnesium, would always challenge the other metal cation, calcium. So let's look at our activity series. Magnesium's right here on the chart, and calcium's right here. Since calcium is higher up on the chart, that means calcium is stronger. So when magnesium comes in to kick out calcium, nothing's going to happen. Calcium is going to block magnesium because calcium is more reactive. So therefore, if calcium will not get kicked out and magnesium replace it, we're going to say that there's no reaction taking place there. And to write that, you could just write no reaction, or RXN for short for reaction. That is an important thing to always check. You always want to check your activity series. Otherwise, you might do an entire problem and all for nothing. The reaction never really takes place because the cation that's in the ionic compound already is already stronger or more active than the loner metal. So keep that in mind. If we look at question number 3, we have magnesium that's going to try and react with zinc. Okay, if that's the case, magnesium is going to come in and kick zinc out only if magnesium is more active than zinc. So let's look to the right here at our activity series chart. All right, magnesium on the chart is right here up top, and zinc is actually a little bit lower. So that means magnesium is stronger or more reactive than zinc, which means that zinc is now going to get kicked out and be by itself, while magnesium moves in and reacts with chloride. So let me write that, magnesium chloride. All right, now that we have this chemical sentence, let's start writing the chemical reaction or equation for it. Magnesium by itself is just Mg. It's not Brinkelhoff. There's not going to be two of them. When we look at zinc and chlorine, they will make ionic compounds. If we look at their ions, zinc always makes a +2 charge, and chloride ion is going to make a -1. So we'll have to keep that in mind when we write out the equation. So magnesium is going to react with zinc chloride. Because chloride has a -1 charge, you're going to need two of them to cancel out with the zinc cation because it has a +2 charge. All right, now I'm going to draw my arrow because it's going to react and leave zinc behind. Zinc by itself is Zn, right? I'll put that in my notes right there. And then magnesium chloride. Let's take a look at their charges before we write the formula. Magnesium is +2, chlorine's -1. So what does that mean? When these two things are created, magnesium, you only need one, but you will need two chloride ions to balance that out. Now that we have that, we have our chemical reaction written out. We do still have to make sure that it's balanced. Remember, it doesn't automatically balance, but in this case, if we look, it looks like everything is already balanced when we check it. So we could just leave it alone, or if you really felt like it, you could throw ones in there. Again, that's not completely proper protocol, but I wouldn't get too upset with you if you threw ones in front of there, just to let yourself know you checked it. But overall, that single replacement went pretty straightforward. Just a reminder, remember that when you have an ionic compound, you do have to look at their charges to figure out how many of each will be in that actual written formula. Don't forget to do that, or you could end up writing the wrong formula. All right, if we look at question number 4, it looks like iron, which has Roman numeral 3, which just means if it does make a compound, we're going to have to make sure that we use iron 3. It's going to come up against lead 2 iodide. So the question is, who is more reactive? Iron on the activity series is right here, and lead is found beneath it. So who is more reactive or stronger? It's iron. So will lead get kicked out of the compound? Absolutely. So that means lead is now going to be by itself. And now iron and iodide will combine. And that's going to be iron 3 iodide, which will be important because we'll want to know the charge on that iron ion in order to properly balance and write the formula out. Okay, so let's start doing notes. Iron by itself, even though it says iron 3, it's just Fe because it's iron all by itself. Lead is the element symbol Pb, and since it has a 2, it means it has a +2 charge. If I look at iodide on my ion sheet, or the fact that it's a halogen, I know it has a -1 charge. All right, so there are my notes there. If I'm going to write this in a chemical reaction, that's going to be iron plus lead 2 iodide, means that I'm going to need 1 lead for every 2 of those iodides, right? So it's going to be PbI2. Now I'm on to the other side. Let's do some notes up top. Lead by itself is just going to be Pb. It's not part of Brinkelhoff, so it doesn't need to be Pb2. And then the last compound is going to be iron 3 iodide. So iron 3 we know has a 3+ charge, and iodide, which we learned from earlier, has a -1. So when you put this all together, lead is going to be formed plus iron 3 iodide. If I have 1 iron with a 3+ charge, I'm going to need 3 iodides to balance out that positive charge. All right, but now that I've done that and everything's written out, unfortunately, this isn't balanced completely. So I do need to figure that out. If I look at my iodides, I have 2 on the reactant side and 3 on the product side. So I'm going to try to make each of those iodides 6. And to do that, I'm going to multiply by different numbers. But now that I have 3 times 2 on the reactant side and 2 times 3 on the product side, I now have my iodides balanced, and now I just have to make sure my iron and lead does too. Well, since this 3 is here, there's going to be 3 lead, so I'm going to put a 3 here. 3 times 1 would give me 3 leads. Since I have a 2 times iron over here, I'm going to put a 2 there. Excuse me, I just hit a wrong button there, but let me put my 2 there. Now that I have that balanced out, I have 2 irons on each side, 3 leads on each side, and 6 iodides on each side for a 2-3-3-2 ratio. And it works out. For question number 5, it looks like barium is going to try and sneak in and kick aluminum bromide out. When I look at the chart, barium is higher up on the chart than aluminum, which means it's more reactive or is more active. So therefore, it's stronger, so barium is going to kick out aluminum. So poor aluminum is going to be all by itself. And that means that barium is now going to combine with bromide. So the new compound will be barium bromide. And sorry for the cramped writing, but I think you have more room on your sheet. Now that we know that, we can start making the balanced equation, or at least end up with the balanced equation, since this is the chemical sentence. Barium all by itself is Ba. That's good. It's not part of Brinkelhoff, so you don't need two of them. Now aluminum bromide, metal and nonmetal, that's an ionic compound. Aluminum has a 3+ charge, and bromide ions have a -1. So I'll have to consider that when we do write the chemical formulas for that. So let's start that. Barium is going to react with aluminum bromide. For every 1 aluminum, since it's +3, you're going to need 3 bromide ions. And that should balance those out, at least for writing the compound. Not necessarily balancing the equation, but the compound. Now over here for my notes, I have aluminum by itself, so that's just Al. But since barium bromide is a compound and it's ionic, I do need to take into consideration their charges. Barium is +2, and a bromide ion is -1. All right, so when I write that chemical equation out, I'm going to make aluminum all by itself, and barium, which has a +2 charge, would hold 2 bromide ions in order to balance out to 0 charge. Now that I did that, I have every compound and individual element written out correctly, but unfortunately that doesn't naturally balance out, and that's okay. We can use coefficients, the big numbers, to do just that. As I'm looking from back here, I see that I've got 3 bromines and 2 bromines, and that's not going to work out. So I'm going to make them both 6 bromides so that they can eventually balance out. So by doing that, though all my bromides on each side, there's 6 of them, and that's balanced, I now made my aluminum unbalanced and my barium. So since I have 2 aluminum over here, I'm going to drop a 2 there to make 2 aluminum. Since I have 3 barium over here, I'm going to put 3 barium right there. Now with the 3:2:2:3 ratio, it is completely balanced and it works out. All right, let's do one more problem together, and then the last couple you can try on your own. I think between videos 1 and 2 with single replacement worksheet 1 and single replacement worksheet number 2, you should have a general foundational idea to be able to try to on your own and be fairly confident, right? It's all about naming and making sure that if the loner individual ion is stronger than the metal in the single replacement compound, it'll kick it out and then you'll swap them. So next up here is hydrogen versus nickel. If you look up on the sheet, hydrogen is down here on the chart and nickel is actually a little bit above it. So believe it or not, hydrogen is a little weaker. So if hydrogen comes and tries to kick out stronger nickel, will anything happen? No, it won't. Nickel's too strong. So that means nothing will happen, so you could say no reaction. And again, RXN is just a shorthand chemistry form for reaction, right? So again, it's just a reminder, though, a lot of these single replacement reactions work. Don't forget to check the chart each time, because you might end up doing something, too much work and balancing out, only to realize later that, oh man, this wouldn't even have happened in nature. So there's no way I should have even taken the time to write that all out. All right? Great job on today, Science Fam. Try those last 2 out for homework so that you can definitely get those done and prove to yourself whether or not you know how to do it or not on your own without videos. Take care.